So there's line coverage, which measures how many lines of source code or assembly you've executed. Branch coverage, which monitors how many branches in a program you've taken. So there's like a little code sample there, and if you think about it, so you can cover each of those lines with just one test case, if like X is 3, because you do that and you do the conditional there. And then if you want to do each branch, so there's 2 branches in that program, it actually takes 2 test cases. So you can see that if you cover branch, if you look at branch coverage, it's a finer grain metric than line coverage. So you get more information. And then after that, there's an even finer grain metric called path coverage. And what that does is it measures all the paths of the program and how many of those you've actually executed. And so there's another piece of code, and if you think about that for a minute, you'll see you can get all those lines covered in just one test case. But there's obviously a lot going on in the code, so that doesn't give you a good idea of what you've done. You can cover all the branches in 2 test cases, and you can figure out what that is. And then it actually takes 4 test cases to go down each path. So that just shows you, how you can, how much of a better measure of path coverage is. However, it turns out path coverage, no one uses this because there's too much information. So if you think about it, and if you think about this last slide, it makes sense. But normally, for path coverage, if you go down, if there's n branches in a program, and it'll generally take 2 to the n test cases to go down all the branches, but it'll take 2 times n to go down all the branches, and 2 to the n to go down all the paths. And if you think about how many branches are in a program, like SendMail, well, there's a lot. So you can't go down all the paths, it's impossible. So people don't even try to measure that. And if you start thinking about loops, it's even worse. So obviously you could have infinitely many loops. There's people have ways around that, but still, it's basically not a good approach. And another problem is there's this thing about infeasible paths. So there's a little code sample, and if you just sort of look at it from a mile away, you're like, oh yeah, 4 paths. And if you had like an analysis tool, it would probably tell you there were 4 paths. But if you think about it for a second, one of those paths can't happen. It's impossible. And so that's something you have to worry about. Alright, so those are different kinds of code coverage. My favorite is line coverage, just because it's easiest, but people choose different things. So there's actually more than these 3. So I claim that this code coverage thing is going to answer a lot of your questions about buzzing. So let me tell you how you get it. We've got source code, it's real easy. When you compile it, you just do something tricky, and it adds some extra code and moves reports your code coverage. If you don't have code coverage, or if you don't have source code, you have to do something different. There's a few approaches you can take. One is you attach a debugger to the thing, and you just monitor what it's doing. And that's basically what PyMay does, and I'm going to show you that later. Another idea is you can do something with virtualization. So you could use like Valgrind. I call it Valgrind. I guess the proper terminology is Valgrind. Anyway, there's actually something in there that'll almost do it already out of the box. A little bit of change, and it would definitely do it. Or you could use like a real virtual machine like Boxreturn. And finally, you could do what compilers that add in the code coverage stuff do by adding instrumentation. You can do that dynamically in binaries too. I've never done that though. Alright, so I'm going to preach to you for like the next half hour about how great code coverage is. But before I start, let me tell you about how it's not as great as I'm going to tell you. So basically, there's some problems with code coverage, and this is what they are. The main thing is, and you'll hear people complain about this all the time, that code, just because code's covered doesn't necessarily mean it's been tested or buzzed or whatever you want to say. And that's absolutely true. So this is an example here, and you can imagine hitting this string copy, and it can be covered, and so you're like, oh, it's covered, it must be safe. But obviously it's not. If you send in a large source, there's a problem. Maybe you covered it with a small source. And all it would have taken is a little change, and you would have crashed with it. So just because code's covered doesn't necessarily tell you that it's been tested well. Another thing that happens is there's going to be a lot of code in a program that isn't covered, but you don't particularly care about it. So there's another little sample code, and basically it's out of your control whether this malloc fails. And there's going to be all this code that's never executed, and it's run out of memory function. But then again, you don't particularly care about that because it's not really under your control. There's going to be a ton of code that you don't really care about, but you may or may not be covering. And which leads you to this idea of attack surface. So the attack surface is the portion of the code that you can actually get executed from either the remote access point that you're looking at, or through reading a file, or through mailing arguments, or whatever you're monitoring. So wherever the attack is coming in, whatever code you can get executed from that is called the attack surface. And so when a daemon starts up, It has to bind to a port, it has to read its configuration file, it has to do a bunch of startup stuff, and that has nothing to do with you attacking it. And so there's going to be some code that's executed, some code that's not. You don't really care about that, because you can't control it. What you really care about is the part that processes the data. And the problem with that is that since you can't, there's no way to really measure the amount of code that is the attack surface. And so when you run your code coverage tool and you say, hey, I covered 17% of the code, it doesn't really tell you anything, because you don't know how big the attack surface was. Maybe you covered every line that was humanly possible. Or maybe you could have covered 90% of the code. You have no idea. So basically, the fact that this is an attack surface means that absolute code coverage numbers are meaningless. All that is useful is if I cover 70%, you cover 20%, you did a better job. That's all I can tell you. But we can't say anything about, if we're done, if we've covered everything we can cover. So now the examples, which that was in the title, so I definitely have to do some examples. I'm going to start with some source code examples, and just because I think it's a little easier to understand, but then we'll quickly move into just assuming you have the binaries and stuff. That's normally what we have in real life. Okay. So, like in the introduction, I found a bug in the iPhone, and there was like a lot of press about it and stuff. But when it was going on, I'm such a responsible guy. I couldn't tell anybody about the bug, and so I couldn't tell anyone how I found the bug, which I think is really interesting. And in my Black Hat talk, I didn't have to. So basically, I never told anyone how I found the bug, but how I found it was with buzzing and code coverage. So code coverage is really what helped me find the iPhone bug. So how did I do it? It turns out that there's this WebKit, which is an open source project that all the Apple internet applications use. So like the mail tool, the web browser, the dashboard, everything uses this WebKit. Actually, some others like Nokia phones or something uses too. Anyway, lots of things use it, and it's open source. You can check it out. That's good. If you surf around on the WebKit website a little bit, you'll see this little thing. It basically says that, hey, it's open source, please contribute code, and by the way, if you're going to contribute code to the JavaScript core code, make sure that you run this test. Oh, that's cool. So now I know what test we need, right? So I can figure out what code they're testing and what code they're not testing. So let's do that. So the tool that I use to look at the code coverage for WebKit is called Toorcon. So it's open source. It was originally made to look at code coverage with Linux kernel, but it works on anything. And the cool thing about it is, unlike Gcode, which most people have probably heard of, it'll compile everything into one file, and it'll make a little HTML report. So it's nice to use, but it's actually sort of a pain. It's a pain to use, but it's nice. So here's how you do it if you ever want to try it. So to build it, you run the script that comes with WebKit with a nice coverage flag, which does everything for you. Run the test suite, and then Alcove falls on itself. So you got to do a lot of things to make it happen. You can figure those out if you ever tried. Then you run this Alcove command, which gets all the code coverage from the test suite that you ran. Then you generate this HTML report with this other Alcove tool called GenHTML. And this is what you get. Hopefully you can read it from where you are. You see my mouse? Okay. So if you look, these are all the directories in the JavaScript core part of the WebKit. If you look over here, you can see how many lines of code are in each directory. So basically, these two directories right here are the ones that have the most code. And if you look, there's one directory. So if you look up here first, the entire project has 60% code coverage. Like I said, that's sort of meaningless. We don't know if that should be 100 or if that's great. But relatively speaking, we can look at these two directories and know that 80% of this directory is covered, and only 55% of this directory is covered. So obviously they did a lot better job testing this code than that code. So just saying that again, 60% of all the lines are covered, 53% of all the code is 80% covered, and 17% of the code is only 55% covered. It turns out that 70% is in the Perl-compatible regular expression code, PCRE. So it was covered way less. I said, hey, let's take a look at that. And I was also sort of excited because, regular expressions are complicated and they need to parse, so it seemed like a good place to look. So we wrote, it was myself and two other guys, we wrote a 20-line Perl script that generated random regular expressions. We ran through the PCRE parser. We just ripped it out of WebKit. Ran it, and it didn't crash. We ran it for a few hours or something. It didn't crash, but we saw all these errors that said something about internal error code overflow. And so we looked in the source code to see what that was. It turns out, like, the line before that, it totally just, like, blindly copied some huge buffer, and it really hurt itself badly, and then it told us about it, which was nice. So this was good. We found a heap overflow, and that was sort of that's how we found the bug. Then the question is, okay, we want to write an exploit for it, and all we know is that with a particular regular expression, we can cause it to overflow by 2 bytes, a particular heap buffer. And if we put more of those particular regular expressions into a bigger regular expression, we can overflow, more of these 2 bytes. That's all we know. And we got our shiny iPhone. We know it's vulnerable because if you start to a web page, it'll crash the little browser in the iPhone. But we don't have a debugger. We don't have any way to compile code for it. We don't have any way to run code on the iPhone. Now you can do all that stuff, but at the time you couldn't. All we have are crash reports, which are basically like little Dr. Watson things. And we had 4 dumps after we tweaked things a little bit. So the question is, well, how are you gonna write an exploit for this, right? It's tough. And so all I do all day is sit around buzzing. So it occurred to me, all we need really is to get control. So we need the program counter, because it's like a little embedded ARM device. And we need to just point to our shellcode, right? So if we can do those 2 things, we're done. Not rocket science there. I do that without a debugger. Well, the same way that I build all my clients while I'm watching TV, I do fuzzing. Alright, so, don't tell my clients that. So what did we do? We wanted to try to fuzz the thing and let that find the exploit for us. So this bracket, star, bracket is the evil regular expression that would overflow a heap buffer by 2 bytes. So all we did was we generated hundreds of regular expressions, just randomly, and we sprinkled in these little evil strings into it. Kept launching the iPhone over and over and over against these bad JavaScript regular expressions. And then of course it crashed a lot. Sometimes it didn't. And we gathered the crash reports. We looked through them and found a good one. 99% of them were just didn't seem important, but eventually we found one that looked good. And this is what it looked like. So here's the program counter. If you disassemble it around there, it looks like it's unlinking some sort of linked list. If you look at the registers that are involved, they look controllable. It turns out they are. So what's that mean? Well, it's just very typical. You control the things in an unlinked linked list. That means you can write 4 bytes anywhere. So what did I overwrite? What sort of data structure was this? Was it heap metadata? Was it some WebKit specific structure I've overwritten? I don't know what it was. I just know it works. And that's the beauty of fuzzing, and that's the beauty of this exploit. I have no idea how it works. So I was able to, so I can write 4 bytes anywhere at this point. The question then is, well, what do I overwrite? And I could figure out something real clever, but I know for a fact that there's going to be addresses on the stack that eventually is going to stick into PC. And so if I could overwrite one of those, that'd be good. With a debugger, I'd be done, but I don't have a debugger. So I need to figure out where on the stack I'm going to overwrite.